The organisers, would like to say a few words of thanks to the Institute staff. It really is a pleasure to organise a meeting here, and that one doesn't have to do any of the administrative detail. The staff are so great at organising it for us. In particular, I mean, there are a lot of staff here, the ones who've been specifically involved in the meeting, Jane for feeding us all tea and coffee and biscuits, and Naomi behind the desk, but in particular, I think also Chia and above all Tracy, with whom many of you will have had communications, have been absolutely great in organising the meeting. So Nick there has some. And then hiding in his little room at the back, and Nick has to get him out somehow. I'm sure he can hear us. But. So Steve, of course, has been our great AV guy who's helped us keep everything going smoothly. Of course, there was a glitch on Monday morning. I have to say that was the first AV problem we've had at all in the whole of the program since I've been here. So Steve and his colleagues have been absolutely great about that. So we've got something to say thanks to Steve for all of his work through the meeting. Charlotte will share the last session.
Okay, so let us start this last session. The first speaker of the last session is Sergey Frolov from Trinity College in Dublin. Speak about string S matrix and bound states.
First of all, I'd like to thank the organizers for the invitation. And the title of my talk a little bit different. Since Gleb Arotunov couldn't come, I will also have to say something about the string S matrix. And you are welcome to interrupt me at any moment you want to and ask any questions you like to ask. First of all, I let myself to skip the introduction because you already heard everything about this. And I'll stop here. And so let's assume that the BS conjecture is the right one, and we know the string S matrix. And then this string S matrix can be used to derive asymptotic beta equations. And these asymptotic beta equations coincide with the conjectured Bicet-Staudacher equations for physical states. They are different from these equations for unphysical states, but at least at this stage, we are not really interested in this subroutine. And then this S matrix also can be used to derive the finite size corrections to the dispersion relation, as Romo Altyanik explained us yesterday. Was it yesterday? And well, the expressions agrees with the string sigma model computations, and that's definitely a non-trivial test of the BS conjecture. So the next step is, of course, to understand the spectrum at finite values of the charge J. And one way to do it is to try to use the thermodynamic beta ansatz idea, which has been already used to explain Rapin effects, again, in this paper. So this is a very complicated problem in our case, because the spectrum, string theory spectrum, contains a lot of bound states, and then the model itself is not Lorentz invariant, and that means that basically the model which is obtained from the string sigma model, from the light cone string sigma model by the double weak rotation, does not coincide with the string sigma model itself. And the thermodynamic limit has to be done for this double weak rotated model. So in what follows, I will refer to this model as mirror model. And since we are not studying here topological string theory, I hope there will be no confusion. So the first two steps, the simplest steps, are to find the dispersion relation, the S matrix for the mirror model, and to analyze the structure of the bound states for the model. And it appears that these two problems are basically related to similar problems for the string sigma model. And by this reason, I will start and will mainly discussing just light cone string theory and the S matrix for light cone string theory and bound states of the string sigma model. So this is the outline of my talk. Well, you could think about the first part as an introduction, which I kept, So I define the rapidity torus, and then we will see that S matrix, the matrix structure S matrix, is basically a meromorphic function on this torus up to the scale factor, which cannot be fixed by symmetries. After that, I will show how the S matrix of the mirror theory can be derived from this one by shifting the complex spectral parameter by quarter of the imaginary period of the torus. And then I will discuss bound states of the string sigma model and finite size corrections to these bound states. And we will see that, in fact, many of these bound states show various signs of strange behavior. In particular, for some of these bound states, the first correction to the energy is complex, which means, from our point of view, that which is from our point of view the simplest indication that the asymptotic beta ansatz cannot be right. And then I conclude with some open questions. So this is the object we are going to discuss. So this is the SU2/2 invariant S matrix, and the string series matrix is obtained from this one by taking the tensor product of two of these such S matrices and multiplying the tensor product by a definite scalar factor. This S matrix, as you see, depends on x plus x minus, which are functions of the momenta P1 and P2 particles, scattered particles. And it also depends on these parameters eta1, eta2, eta1 tilde, and eta2 tilde. And these parameters are defined here. And for this S matrix to be the S matrix of the string sigma model, these parameters etas must be of this form. There is no degree of arbitrariness. These parameters etas are just fixed uniquely by some requirements, such as Young-Baxter equation and generalized unitarity condition for the S matrix. So the S matrix used in spin chains corresponds to eta equal to 1. And this S matrix does not satisfy the Young-Baxter equation. Any question here? No, no light constraint action. I have just 40 minutes, and I will need at least 1 hour to explain how it is related to the light constraint action. So it is related. You take light constraint action and you compute the scattering S matrix, and then you expand the S matrix I have just shown you in powers of 1 over G, and you reproduce the right result. This S matrix is obtained by using symmetries, and it was obtained by Bicert. So I do not really want to discuss how it was derived. So it is given, and we want to analyze this S matrix. As you have seen, this S matrix is written in terms of x plus minus variables, and they're related to the momentum of scattered particles by this formula. X plus over x minus is e to the I pi, and they also satisfy this quadratic relation. And I will be using as a coupling constant the string tension G equal to square root of lambda over 2 pi. And then we know that the dispersion relation is of this form. And also we know from Yannick's paper on crossing relation that this equation implies that the real rapidities take values on a torus, on an elliptic curve. So the simplest way to get the torus is just to solve the dispersion relation by using these elliptic functions. And well, I will be using mathematical notations for elliptic modulus. It would be probably better to use the letter m, but well, I don't like the letter m. I'm always confused whether it is a mass or mode number. So I will be using the letter k for the elliptic modulus of these functions. And then once we use this representation in terms of elliptic functions, we see that real values of z corresponds to real values of momenta p, and the energy E is positive in this case. So this torus has two periods, one real omega to omega 1 and one imaginary period to omega 2. Okay, then by using this parameterization, we can express x plus minus in terms of this elliptic function by this formula. And we see from this formula that x plus minus, the absolute value of x plus minus is greater than 1 for real values of z. And also that imaginary part of x plus is greater than 0 and imaginary part of x minus is less than 0, again for real values of z. So let me repeat again that real values of z correspond to real values of the momenta p. Then the dispersion relation in x plus minus are in fact periodic with period omega 1, not to omega 1. And that means that the kinematic region in the z plane is not from minus omega 1 to omega 1, but from minus omega 1 over 2 to omega 1 over 2. And that corresponds to this range of the momentum p, from minus pi to pi. Okay, and finally, if you look just at this equation, then we see that each solution of this equation corresponds to a point in this torus. So I will be using these strange numbers in the imaginary direction, in the y direction, in the z plane, just for visual reasons. Okay, and then also analyzing the map between x plus minus and z, this representation and the relation of the momentum p to x plus x minus, we can see that in fact the complex p plane is in one-to-one correspondence with a half of a torus, not the whole torus, but a half of the torus. Okay, so if you look at this constraint, we see that if x plus minus solves the constraint, then these three pairs of numbers also solve the constraint, because we can exchange x plus and 1 over x plus in this equation. And by this reason, we can actually divide the torus into 4 non-intersecting regions in 2 natural ways. The first way is by curves x plus minus is equal to 1. And the second one is by curves imaginary part of x plus minus is equal to 1. Because of this fact, it will be mapped one to another. So this is how this torus looks like if we use these curves. So these are the curves x plus minus are equal to 1. And well, this is the real z-axis. So the real values of the momenta correspond to these values of the complex z coordinate. And well, we rescaled also the coordinates z, so that the range of x and y would be from minus 1 to 1, I think. At least the range of x would be from minus 1 to 1, the range of y also from minus 1. No, from minus 4 to 4, and minus 1 to 1. Yeah, so the absolute values of x plus minus are greater than 0 in this region, in this fish. And most probably it is the physical region of the string theory. We will see some evidence in favor of that later. And then there is a second division of the torus by the curves imaginary part of x plus minus is equal to 0. And in fact, this leaf here most probably is the physical region of the mirror model obtained from the original one by the double weak rotation.
What do you mean by this?
Yeah, that's a good question. Basically, this is the region where we would like to look for bound state for solutions of a bound state equation. So
Bound state depends on 2 momenta, not just 1.
Right. So it is a physical region with one, for one variable. Both variables p1 and p2, z1 and z2, should lie here in this region. We do not have a proof of that, and in fact, in non-relativistic theory, we cannot prove this because there is no one-to-one correspondence between S matrix and scattering potential. But this looks like the best choice, and I will discuss this later. So this is the intersections, and the points of intersection of these curves are actually very interesting points, and many strange things happen exactly at these values of the complex momentum. Okay, so these regions depend. The shape of these regions depend on the values of the coupling constant of string tension. In particular, when the string tension is small, we see that this region here in rescaled coordinates becomes basically a rectangle in this region. And when the string tension becomes very large, it becomes a rectangle of this form. And moreover, actually, the region restricted by curves x plus absolute value of x plus minus is equal to 1 becomes basically the same as the region restricted by curves imaginary part of x plus minus is equal to 0. 1 is obtained from another one just by a shift by a quarter of an imaginary period. And it's not surprising, in fact, because in the strong coupling limit, when g goes to infinity, well, weak coupling limit. In string theory, it is a weak coupling limit. The model becomes relativistic invariant, and by this reason, it should
the
be
momentum is very small, right? The excitation
Yeah.
that it comes from.
Exactly, yeah. So the dispersion relation becomes the usual one. Okay, so I actually need to speed up. So this was the rapidity torus, and these are the points of intersection, the coordinates of the points of intersection of these curves. And these points, the origin of these points is easy to understood if we consider a rapidity variable u, which is defined by this formula. And this is expressed again in terms of elliptic function by these formulas. And then if we solve this equation for x plus or for x minus, we will find the square root here. And these points corresponds to zeros of the square root. So to branch points of the map from u plane to x plus 1 plane. And well, we need also to have some cuts, and there are many different possibilities to choose cuts. So we can connect these points by different lines, and it will correspond to different maps of the u-plane onto the z torus. So in particular, here is the case of the string theory map. So we have u-plane and we have this torus. And if we choose the cuts, as shown here, so well, here are the lines, and the green line here is mapped onto the green line here. And actually this line is mapped here, and that one is mapped here. And then we also see the yellow line, this cut here, it is mapped here, and the red one is mapped there. So once we choose the cut, say the cut from this point to that one, and this point to this one, we have a one-to-one map of the u-plane to this fish, which is the region corresponding to absolute value of x plus minus greater than 1. If we would choose the cuts differently, we would get some other maps of the u-plane onto the z torus. In particular, if we would choose the cuts going from minus infinity to this point, from infinity to these points, we would get a map from the u-plane onto this leaf restricted by the curve imaginary part of x plus minus equal to 0 here. So the map depends on the choice of your cut. Okay, well, so as I said, u-plane is mapped onto 1/4 of a torus. So to cover the torus, we need to have 4 planes. Well, and this is just a picture to show how you need to glue these u-planes to get the torus. It is just one of the possibilities. Okay, so complex p-plane is also mapped onto the u-plane, and in this case it is mapped twice. And for real values of p, this map can be written in this form. So this square root explains why it is a double map. So again, in the limit when g goes to infinity, this relation becomes u is equal to, and well, we need to rescale u, and then the relation becomes u is equal to cotangent p over 2. And this is the usual relation between the rapidity and momentum variables of the Heisenberg spin chain. So this is the spin chain field theory limit. So this is actually a very nice fact, and from that we could just conclude that this fish, x plus minus greater than 1, absolute value of x plus minus greater than 1, is a physical region in the complex z-plane. And there are many reasons to believe that it is the case, because for example, the dressing phase is well defined exactly in this region. In all other regions, we have to use analytic continuation to determine the tracing phase. Then, as I just said, there is a one-to-one map to the u-plane with the cuts. Actually, to the z-plane, sorry. To the u-plane. So this fish is mapped to the u-plane. One-to-one map of this region to the u-plane with cuts. And then another reason is that in this case, we will have only one m-particle bound state, BPS bound state in the region, which is also nice. And well, we're also interested in the situation. Well, if you take the limit g goes to infinity, so the weak coupling limit in the string theory, then this region degenerates in this strip here, and this is just the physical strip of a relativistic field theory. Again, it is a strip just for one rapidity variable, for one particle. In a relativistic field theory, we usually take a difference. So if you take a difference, we actually get the usual region from 0, when theta changes from, imaginary part of theta changes from 0 to pi. Okay, the only disadvantage I can think of is that it does not cover the whole p-plane. So some values of the complex momenta p are not there, which is very unusual. It is not the case for a relativistic field theory. So then we can, of course, consider as a physical region half of the torus, which is mapped to the complex p-plane. And again, in this case, well, it is a one-to-one map to the complex p-plane, so all complex values of the momenta are covered. And then this region also degenerates to the same strip, physical strip of relativistic field theory. There are, however, disadvantages. The first one is that the dressing phase is not well defined in this region. And then, in this case, we will have two m-particle bound states instead of just one m-particle bound state.
Why do you say that?
You just count the number.
How?
Okay. Yeah, that's a good question. We will have two solutions of the bound state equation, okay? So we would have two apparent m-particle bound states. We don't really know if they are bound
Just
states.
poles in the S
Poles.
matrix.
Poles in the
Those
S matrix.
always correspond to bound states.
Yeah, but in the u-plane, there is no difference between these two poles. They are absolutely identical. Okay, and then this region also does not reduce to the physical region of one loop gauge theory spin chain, which is, I'm not sure it is really that bad, but probably it's better to have the same region for g equal to 0 and g not equal to 0. And finally, we can also take a very strange choice. We can just say,
sorry.
well, yeah.
You say it doesn't reduce, so it reduced to what?
Yeah, that's a good question. So there will be some external area. Well, you just will not be able to see the full region in the weak coupling theory.
Yeah.
Yeah. So the part that is not in the fish will not be seen in perturbative field
But it's
theory.
present in the
Is it present? I don't know. Can you construct any operator which would have such behavior? I have no idea how to construct such an operator in field theory. It will be related to the discussion of bound states. So still, we can actually make even this choice. We can just say that we will be looking for all solutions everywhere on this torus, and we will just require that the energy of this solution is positive. Why not, after all? But then, yeah, the only advantage actually I see is this one, that each solution of this constraint will correspond to a point on the torus. But the disadvantages, there is a huge number of disadvantages, so I personally do not believe that it is the right choice. And well, let me just skip the discussion of this case. Okay, now a couple of words about this double weak rotation and the mirror theory. As soon as we have the z parameter, the story actually becomes very simple. So we have to exchange, as Romuald explained yesterday, we have to exchange the energy and momenta. And so if we denote p tilde by p tilde the momentum of the mirror theory, then it will be related to the energy by this formula, or expressed in terms of the elliptic function by this formula here. And then we will just need to find the values of z for which this mirror momenta, p tilde, is real. And we can easily find out that all we need to do is to shift z by the quarter of the imaginary period. And this is absolutely the same case as it is done in usual relativistic theory, because there to exchange momentum and energy, we need to shift the rapidities by I pi over 2, which is exactly quarter of the imaginary period. So it is very similar. Basically, there is no difference. Yeah, and then, well, actually, it's possible also to find out that this region, imaginary part of x plus minus less than 0, contains only one empirical bound state of the mirror theory. So by this reason, it is natural to expect that this is the physical region of the model. So let's take a look at this S matrix again. Now we know everything about x plus x minus in terms of the complex z variable. And still, well, we need to say something about this ethos. And the nice fact is that these ethos are also meromorphic functions on the z torus, because exactly this, well, first of all, e to the ip over 2, it is just this combination here. Remember that p was equal to amplitude of z, so e to the ip over 2 is just given by this formula here. And the nice fact is that this parameter eta of z, this combination, appears to be equal to this elliptic function, which depends not on z but on z over 2. And well, by using these formulas now, these expressions for the parameters eta, we can think about this S matrix as a matrix on a complex z plane or on a complex z torus. We can replace p1 and p2 by complex z variables, z1 and z2. So after that, we find out that the S matrix I have shown you satisfies all these nice properties. First of all, it satisfies the Young-Baxter equation. Then it satisfies the normal unitarity condition. It satisfies the generalized unitarity condition. This condition just reduces to the usual physical unitarity condition if z is a real variable. And well, actually, the usual unitarity condition and generalized unitarity condition imply this relation for the S matrix, and it is called Hermitian analyticity. All these requirements hold for usual relativistic series, integrable models, two-dimensional integrable models. The only difference is that this S matrix depends on two parameters instead of just on the difference of these parameters. And the claim is that these three conditions fix the form of the S matrix uniquely up to a constant rotation.
Excuse me, you don't take into account the dressing factor?
Yes, up to the dressing factor. I'm discussing SU2/2 invariant S matrix. I'm not discussing the string series matrix. So this is valid for the S matrix I have just shown you, which is this one, all these properties. And I'm using, as you see, capital S letter to denote this S matrix. So this S matrix satisfies these monodromy properties. So in fact, it is periodic with period 4 omega 1 and 4 omega 2. And the nice fact is that the graded version of this S matrix coincides with Shastri's R matrix for the Hubbard model, again up to a scalar factor. So they differ only by a scalar factor. And that means that basically Shastri's R matrix is also a meromorphic function on a torus. As far as I know,
it's not that straightforward. You have to take two limits, and you will restrict yourself unto two points in the x plus minus space for Shastri.
No, I don't have to do any limit. It just is direct relation up to a scalar factor. So you take the S matrix. You take this S matrix, and you write the Shastri's S matrix in a similar form. Then you take this element of the Shastri's R matrix, you divide it by Z1, and you should get minus of this one. And this is the relation.
But then you have to solve these 10 equations, right?
It's solved. It's an explicit form. Everything is solved here. X plus x minus is a function of z. Eta is a function of z, as I have just shown you.
Really?
Everything is solved. It is an explicit expression. It is an explicit function of z1 and z2. It is a meromorphic matrix function on the torus. Okay, so as I said, it's SU2/2 invariant S matrix. So if you want to have string S matrix, we need to multiply it by a scalar factor and then to take a tensor product of this two S matrices, and then we can see that it satisfies the crossing relations and well derived by Romuald, but I don't want to discuss it because it's not really that interesting here.
And it's no longer single valued on the torus.
Yeah, and it's not single valued on a torus. So the scalar factor breaks this condition of meromorphicity. Okay, so let me maybe mention one fact about this mirror theory, because the S matrix of the mirror theory must be also a unitary matrix for real values of the shifted parameter z. And the nice fact is that you can really easily prove that this S matrix of the mirror theory, so it is obtained from the string theory S matrix just by shifting the parameters z1 and z2 by the quarter of the imaginary period. And then you can really check that it also satisfies this S tilde matrix, satisfies the generalized unitarity condition for the mirror S matrix. And this condition in fact follows from this identity here. We shift both z1 and z2 by the half of the imaginary period, and we get the same S matrix. And this is in fact a consequence of crossing relations for the S matrix. So in some sense, the unitarity of the mirror theory follows from the crossing relations of the string theory, and vice versa. The interesting fact is that the dressing factor in the mirror theory is not unitary anymore. There is, however, a unitary combination of a dressing factor and some factors of x plus, x minus, and I will show you very soon. So, bound states. So, we are going to discuss string theory bound states. And as you know, bound states corresponds to complex values of momentum, and they correspond to poles in the S matrix. And well, if you consider beta ansatz equations, then they correspond to so-called beta strings. And bound states of the string sigma model have been discussed by Dori. So that's what they discovered. They discovered that the m-particle bound states belong to a short atypical representation of the centrally extended algebra, symmetry algebra. And they also, in this paper, they also argued that additional simple and double poles of the S matrix do not correspond to new bound states. Well, in fact, if you take a look again at this S matrix, then these poles are this one, x1 minus minus x2 plus. Well, this is never equal to 0. So actually, in this form, you do not see any additional poles. All additional poles come completely from the dressing phase, the scale effect to be precise. So what they showed that these poles do not correspond to bound states, and by this reason, I'm not going to discuss them. Okay, then these bound states exist, in fact, for all values of the bound state momenta. But, well, depending on the choice of the physical region, we could have either one bound state, two bound states. Oh, again, I'm talking about solutions to the bound state equation. I will show you it in a minute. Or 2 to the power m minus 1 m-particle bound states. And all these bound states, all these solutions, they have the same set of global conserved charges. The charges take one and the same value for all of these solutions. And that basically means that we cannot distinguish them, at least when j is equal to infinity. So we would like to analyze these bound states, and we would like to answer to the question whether the fish x plus minus greater than 1 is the physical region, because it is the only region which contains only one bound state here. Or maybe, in fact, some other region is the physical region, say half of the torus, the complex p-plane. But then it would probably be a sign of some hidden symmetry, because it would mean that the spectrum is degenerate, and, well, we don't know what would be the origin of this degeneracy. So what we do, we consider bound states in SU2 sector of the AdS5 cross S5 series. How much? Just 5 minutes? I'm just started. So we take these complex values of the momenta p, p1 plus p2, but we allow q, this parameter q, to be imaginary. All we require is that the real part of q to be positive. Okay, and then the bound state energy is computed by using the usual formula, and it must be, of course, positive if it's a physical particle. So we take the first equation, beta equation in the SU2 sector. It has this form, and sigma here is this combination. And this combination is, in fact, unitary everywhere. It satisfies the generalized unitarity condition. So it is unitary in string theory, and it is unitary in mirror theory. In fact, I guess that this combination should be called the dressing phase. And by using this sigma, the equations are written in this form. And notice, by the way, that the left-hand side depends on j. There is no L here. There is no length of spin chain. So j is the charge, which corresponds to the isometry of the 5 sphere, and
J is L plus M.
no, j is j. Just the charge.
Just the charge.
There is no L. There is no j plus m. It's just j. It is the circumference of the circle on which the string sigma model lives.
This is a feature of the gauge you've chosen.
No, it's a general feature. It's just a consequence of the form of the S matrix. As I told you, the beta equations derived by using the SU2/2 invariant S matrix coincide with the Bisset-Schoedach equations only for physical states, which means only for states with zero total momentum up to a multiple of 2 pi. So these equations are equivalent to the right equations if the total momentum p is equal to 0. If not, then these are the equations as they look like. And there is no L here. Okay, so, well, how we find the bound state equations? So actually, Joe explained to me how we find bound states. Here, so we just consider the situation where j goes to infinity. A real part of q is supposed to be positive, so this term is exponentially divergent, and therefore the denominator must be equal to 0, and therefore we must have one of these solutions. We must have one of these equations to be satisfied. So this equation corresponds to unphysical pole.
It's not
act-
physical, it corresponds to T-channel
Yeah,
extreme
T-channel.
state.
So if we restrict our attention to the fish, there is no solution to this equation there. So it's not even in the physical region. That's another reason why the fish is a good choice for the physical region.
Interpretation doesn't match the usual one. In the
Yeah.
statistical theory.
Okay. So this is the bound state equation, and that's the equation we are going to solve. And this, again, the equation which was analyzed by Nick. And it leads, as was shown in these papers, to a two-particle BPS bound state with this energy. And in fact, we can write down the very explicit solution to this equation. So this is, in terms of this variable t, this equation can be written as a polynomial of degree 4 in e to the power q. And this equation can be solved, and this is the solution. The solution, as you see, very explicit. And when you look at this equation, and by the way, let me notice that this square root is very similar to what Joe had today. This sign to the force in his formulas. So when we look at this formula, we see immediately that q is real only if the expression under the square root is positive. And this is positive only if the momentum is less than some critical value, which is determined by this formula here. And then there are also two solutions with real values of q plus and q minus, but only one solution q minus with small values of q minus, what is minus 1? Lies inside this region, x plus minus greater than 1. So the second one x plus lies outside the region, but inside the region corresponding to the complex P plane. Well, since I don't have any time, so I don't know what to say. So if P is greater than P critical, that will be the story. As you see, the real parts of momenta P1 and P2 are going to be different. And both of these solutions will lie exactly on the boundary of this region. Absolute value of x plus minus is less than 1. And again, there will be two solutions, and it will be necessary to choose one of these solutions. And it looks like that this choice is related to the parity symmetry of the model, but we do not really understand the details. So that's how this looks in the z-plane, the bound state solution looks. So this is the values of z1 and z2 for values of the momentum p less than p critical, and these two curves are symmetric, as you can see. But once we reach this point, and this is the point of intersection of the curve imaginary part of x minus is equal to 0 and absolute value of x minus is equal to 1, then we will have two different choices. We could go either this way and that way, or we can go this way and this way. The solutions are not complex conjugate anymore. The momenta are not complex conjugate. And, well, this is one of the possibilities to connect all these curves together. In particular, if we start with the momentum minus pi at this point and move along this curve, and this would be the momentum of the first particle, then the second particle will have a closed loop in the z-plane. Well, And this, by the way, corresponds exactly to the picture we have already seen, a map of the U-plane onto the Z-torus. Unfortunately, I don't have time to discuss bound state, finite size corrections to the bound state. Let me just say that the finite size corrections to these bound states appears to be complex for the solutions with the momentum p exceeding the critical value, and that could mean two things. The first thing is that there are no bound states for p greater than p critical, and well, it's hard to believe in this, as was explained to us by, in particular, Nick in Saclea, because this is a BPS bound state. So we expect that it would exist for any value of the momentum p and any value of the coupling constant g. So if it exists for any value of the coupling constant g and any value of the momentum p, then that means that the asymptotic beta ansatz cannot be used to analyze the finite size corrections, and it has to be modified. Well, in fact, it's possible to analyze the finite size corrections for all other solutions, and it appears that only the solution corresponding to p less than p critical, this one, is a good solution in the sense that the asymptotic beta ansatz can really be used to study, to analyze finite size corrections to these bound states. The solution that lies here, corresponding to Q plus, which is outside this fish, cannot be analyzed by using the asymptotic beta ansatz, and these solutions also cannot be analyzed. Well, I'm sorry it took more time, and I didn't cover half of what I wanted. Well, on the other hand, it was supposed to be 2 talks. So in any case, I'd like to stress that the superstring S matrix shares most of the usual properties of the S matrices arising in relativistic two-dimensional integrable models. And the construction of this S matrix is absolutely analogous to the construction of the S matrix in any integrable two-dimensional model. We just use the approach used by the Molodchikovs 30 years ago. We use the symmetry and find the S matrix. And then, well, I'd like to stress that the choice of the physical region seems to be extremely important here, and the best choice from our point of view is the one corresponding to the real part of x plus, to the absolute value of x plus minus greater than 1. Only in that case we have reasonably well-behaved solutions for finite values of G for large, but finite values of J. Okay, thank you.
Okay, thank you. Questions?
Is it possible to say, just for somebody who knows nothing, what's the basic features of the light cone string action that aren't implied by the symmetry?
The symmetry
No,
of
the symmetry
the light cone Hamiltonian.
So why do you need the light cone string action? All you need to know is the symmetry.
Of course, we don't need it. It's as I said, it's the usual approach in integrable two-dimensional models. You have a model. You are saying, well, it's classically integrable. Let's assume that it is integrable on the quantum level. This model has definite symmetry, so this matrix must be invariant under these symmetries.
You don't need to use the light cone Green Schwarz.
No, you just need to know that there is this light cone action, light cone Hamiltonian, and this Hamiltonian commutes with charges, with the superalgebra. After that, you can fix the S matrix up to the scalar factor. You need the light cone gauge only to determine the scalar factor, and you can do it in perturbation theory up to some, well, pretty low order, honestly speaking.
It's best to get some sort of phenomenological S matrix when you don't. I mean, eventually we would like to prove that this model is quantum integral.
Well, to prove, there are many S matrices in two-dimensional integrable models, and there are just a few proofs that this S matrices really.
Yeah, but I mean, I think one should turn it around. I mean, in those models, in some sense, they were also not fully solved. But here, maybe there's a better chance actually.
To solve the model.
It looks more complicated, but it has more symmetry. Just like n equals 4 itself. It sort of looks more complicated than most gauge theories. It has all these extra fields, but it has more symmetry.
Sure. But
Question from Prof. Yes.
But you have an impression that this model is still some effective model, and you have no chance to construct the TBA where you have to know everything about all bound states, all energies.
that's right. That's why I'm studying bound states.
Yeah, and one has to really discover some hidden variables. Right. It will not work with.
Actually, the computation Romuald did with this giant magnon, it seems to show that these are the right variables, right? Degrees of freedom. He got the exact factor, I don't know.
Corrections.
Well, actually, the fact that there are infinitely many bound states indicates that there may exist some hidden three-dimensional structure for this model. Yeah, but again, it's not clear. I would say that we definitely have to count all bound states if you want to implement the TBA program. So we need to know this matrix for all m particle bound states. But do we have any extra degrees of freedom? It doesn't seem to be the case. It looks like everything we have is already there. Actually, even more than in perturbative field theory.
So let's
Yeah, by the way, maybe I mentioned for people who are doing perturbative field theory about this state. Oh well, sorry, it's mirror theory. So if you take this point here, the bound state corresponding to the momentum p equal to pi, then it is always in the region p greater than p critical. And this region cannot be seen in the perturbative field theory. Still, this bound state must, you can consider a state which corresponds, say, for the usual magnon soliton moving with the momentum p minus pi, and this bound state which moves with the momentum pi. So the total momentum would be 0. And that would be a nice gauge invariant state in string theory. In field theory, we would not be able to see it because when g goes to infinity, this guy just decouples. So the question is how to construct a gauge invariant operator in perturbative field theory which would describe such a state. And I do not think actually that perturbative field theory contains everything.
Okay, let's
Okay.
thank the speaker once more.